Hi everyone. So I didn't get a ton of feedback about whether you preferred the video with the you know chapters in it or you preferred the Zoom session. So since I didn't get a lot of feedback, I figured I would make the video because it allows me to make it in advance and allows you guys to see it a little bit earlier. So I'll send this to you at the end of this week. So basically, I'm going to go over the problem set for the third and final hour exam. Remember that the final exam is cumulative and it includes both the first three exam material as well as chapter 18, which is relatively short. The homework is relatively short and the lectures are relatively short, but that's also included on the final. And essentially, you're going to have to do the final on Wednesday and Thursday because the class ends on Thursday. So normally you have the tests during the week, but for the final exam, you're going to have the test on Wednesday and Thursday. So specifically, exam 3 will be on Friday till Sunday, as usual, but the cumulative final exam will be Wednesday 8/12 to Thursday 8/13. So you only have the 2 days to take it. And the reason for this is the class ends on Thursday, so we can't have it over the weekend like we normally do. The final exam is a double test, so it'll be about 40 questions with a couple of bonuses, so 42 or 43 questions. And basically, if you get 2 or 3 wrong, you'll still get 100 on the exam, and that's basically how it works. And it'll roughly evenly represent the chapters 12 through 18 that we covered in this course this semester. So that's basically that. And now what I'm going to do is get right into the review set here. So it says, which of the following statements is true? It says a spontaneous reaction is always a fast reaction. This is definitely not true. Spontaneity, or delta G, doesn't tell us anything about the kinetics or the rate of the reaction. So a spontaneous reaction can be fast or it can be slow. In the lecture, I gave the example of a diamond spontaneously turning into coal. A diamond will spontaneously turn into coal, but it might take 1,000,000 years. Sorry, I'm making up the time frame there, but it's an incredibly slow process. All right, the second answer is the answer, so let's look at number 3, C. It says the entropy of the system always decreases for a spontaneous process. The entropy of the universe always increases for a spontaneous process. That's true, and that's the law of thermodynamics. But basically, the entropy of a system can increase or decrease for a spontaneous process. Remember that if the entropy of the system decreases for a spontaneous process, then the entropy of the universe still must increase, which is done, I should say, by giving off heat energy. So that dispersal of heat increases the entropy of the universe. So the entropy of a system always decreases is wrong because of the word always. Sometimes it does decrease and sometimes it does increase, but not always one way or the other. Letter B, because letter D is just none of the above are true. There is a heat tax for every energy transaction. And at the beginning of the 16 lecture, I called this an energy tax. So sometimes they call it an energy tax or sometimes they call it a heat tax. So we looked at the example of coal running a coal generator. And when you burn the coal, that heats up the water that can turn the turbine, but also going out the exhaust is hot air. So when we convert from energy from one form to another, we lose energy, and we lose that energy in the form of heat. So the answer here is choice letter B. Number 2 says, blank is the thermodynamic function that increases the number of energetically equivalent ways to arrange components of a system to achieve a particular state. All right, this is the definition of entropy. So we kind of think of entropy practically as disorder. So if you take the nice ordered house and you let it sit there and you don't fix it up, it becomes more and more disordered, as we talked about in the lecture. But this is kind of the physics way of saying that. Free energy is essentially the capacity to do work. heat of reaction, or enthalpy of reaction, is basically heat energy, and this is just specifically for a reaction, okay, and this is more generally. And molar equivalence kind of has nothing to do with this. Number 3 says, which of the following processes shows a decrease in entropy of the system? So decreasing entropy means that things become more ordered. In the first question, or letter A, we have potassium bromate becomes potassium ions and bromate ions. In this case, entropy is increasing. The solid is more ordered, and the ions floating around in solution are less ordered. All right, here we have CoBr2. Okay, gas becomes CO gas and Br2 gas. So we have 1 mole of gas forming 2 moles of gas. So in this case, it becomes more disordered because we had 1 mole and now we have 2 moles. In this case, we have methanol, liquid, and it becomes carbon monoxide and hydrogen gas. In this case, we have 1 mole of liquid becoming 3 moles of gas. This is more disordered, and this is more ordered, so entropy is increasing. In this case, we have 2NO plus O2 yields 2NO2. In this case, we have 2, 3 moles of gas on the reactant side, and we only have 2 moles of gas on the product side. So 3 moles of gas becomes 2 moles of gas. Here we have a decrease in entropy. This is more ordered because it's only 2 moles of gas flying around. This is more disordered because it's 3 moles of gas flying around. So the answer here is choice letter D. Question number 4 says, consider a reaction that has a negative delta H and a positive delta S. Which of the following statements is true? So we need to remember, because we're being asked about the spontaneity of this reaction, that the spontaneity is related to delta G, the Gibbs free energy. And if delta G is negative, the reaction is spontaneous. So delta G equals delta H minus T delta S. So if we look at this, and we're told that delta H is a negative value, and that delta S is a positive value. So in this case, we're going to have a negative minus something, because this is going to be overall positive. It's not going to be plus something. Why? Because delta S is positive, and this is absolute temperature. So the lowest absolute temperature is 0. So this value has to be positive, so it's going to be a negative minus something. When you have a negative minus something, it's going to be negative independent of what the temperature is. So in this case, for choice letter, it's choice letter A. This reaction will be spontaneous at all temperatures. Delta G will be negative at all temperatures because we have a negative minus something. This reaction will be spontaneous at high temperatures. So I know these aren't the right answers, but I figured we could go through each one of them. So let's take a look at when it'll be spontaneous only at high temperatures. In this case, that would mean that this value we want to be greater, because high temperature means high T, and therefore it means high T delta S. So when this is negative, this is positive. So at high temperatures, if delta S is a positive and delta H is a positive, it means that although it requires heat energy to make this reaction happen, okay, we're going to gain so much entropy that overall it is spontaneous. The reaction will be non-spontaneous at all temperatures. When is it going to be non-spontaneous at all temperatures? This being positive. Well, if delta H is positive and delta S is negative, you're going to have a positive plus something, because you're going to have a negative times a minus. So you're going to have a positive plus something, and this will be positive independent of the temperature. So in this case, it's going to be non-spontaneous at all temperatures. The reaction will be non-spontaneous only at high temperatures. So in this case, it's going to be the opposite of this case. So if we have a value here of delta H, which is negative, that's going to favor this delta G being negative and spontaneity. But if it's non-spontaneous at high temperatures, it must mean that at high temperatures, this minus T delta S actually overwhelms the negativeness of this delta H. Said another way, we have plus something bigger, because negative times negative gives you plus something bigger than this is negative. So if delta S is negative also, then at high temperatures it'll be non-spontaneous. Said another way, it will be spontaneous at low temperatures. You'll also notice that this is exactly the opposite of choice letter B. So this, I hope, gives you an idea of all the cases and the relationship between delta H and delta S. Number 5 says, for the following example, identify essentially the signs on delta H and delta S. So let's take a look at this. We have water liquid becoming water solid. So what are we doing here? We are freezing water. All right, so we need to think practically about what we're doing. This is becoming a liquid, or it is a liquid, and it's becoming a solid. So let's think about whether or not delta H and delta S are positive or negative. Well, if we think about liquid water, do we need to put energy in, heat energy into the liquid water to make it freeze? Said another way, if we have to put heat energy in, then delta H would be positive. Or do we have to take heat energy away from the liquid water to get it to freeze? Well, the water here is the system, and we have to take heat energy away. So with respect to this water as a system, delta H is negative. We have to take heat energy away from water to get it to freeze. What about delta S? Here we have a liquid and here we have a solid. In this case, we consider the liquid as having more freedom or as being less ordered than the solid. So the solid has less freedom and is more ordered. The liquid has more freedom and is less ordered. So in this case, we go from something that's less ordered to something that is more ordered. So we have decreased the entropy because this is less ordered and this is more ordered. So we made it less random. So delta S is also equal to a negative. That is choice letter A. Question number 6 says, below what temperature does the reaction become non-spontaneous? And we're given the reaction, and we're given the value of delta H, and we are given the value of delta S. So what we need to remember is that delta G equals delta H minus T delta S. And in this particular question, it's asking us for temperature. So T is the variable. But we need to know when it becomes non-spontaneous. So how are we going to figure that out? Well, when delta G is a positive value, it's non-spontaneous. When delta G is a negative value, it is spontaneous. So if we set delta G equal to 0, the point where between positive and negative, we can find where the temperature flips it between spontaneous and non-spontaneous. It's also important to remember that if we look at the delta H and the delta S, they're both positive. So this reaction is going to be spontaneous at high temperatures, as we talked about in question 4. So I'm not going to go over that again. So delta G is 0. That's the flip between positive or negative. Delta H is given, and delta S is given. But you have to be careful because delta H is in kilojoules and delta S is in joules. So we need to divide this by 1,000 and put it as 0.2875 kilojoules per K. So we have kilojoules and kilojoules, just like we did in the homework. So 0 equals 136.5 kilojoules minus T times 0.2875 kilojoules per K. All right. So what we would want to do is basically take this, subtract it from both sides, and then divide by the negative of this. And what we end up when we do that is T is equal to 475K. So 475K is the tipping point. Above 475K, this reaction is spontaneous. Below 475K, this reaction is non-spontaneous. All right, so this 0 is the tipping point. Since this is positive, we need this T delta S to be negative enough to make this overall negative. And that happens when we're above 475K. So 476, for example, times this will be a larger negative number than this is a positive number. However, at any temperature below that, say 474K, this is going to be too small. So when we subtract it, as compared to this one, so when we subtract it, we still get a positive number. So this is the tipping point. And the answer here is choice letter A. Number 7. I wouldn't put number 7 on the test. It just brings up a concept that was briefly mentioned in the lecture, but isn't super focused on. It says place the following order in decreasing molar entropy at 298K. And then we're just given a bunch of compounds. It turns out that the higher the molar mass of the compound, the greater the entropy that it has. So here, chlorine has a greater molar mass and therefore a greater entropy than does fluorine, which is the second biggest, right? Chlorine's below fluorine. And then hydrogen, which is the smallest, all right, only has a molar mass of 2, is the last. So this is choice letter C. Again, I won't put a question here where molar mass on the exam, where molar mass is the only factor, because generally speaking, there can be other factors and that also include the shape of the molecule. For these simple diatomic molecules, this molar mass phenomenon does work. Number 8 says, calculate delta S reaction for the following reaction. And then it gives us the standard entropy for each of the species below. So delta S naught for the reaction is equal to the summation of N, the number of moles, because this is in joules per mole, of S naught of the products minus N S naught of the reactants. So this is just like the delta H equation you probably learned in General Chemistry 1, products minus reactants. Now, keep in mind that this works because this is a state function. So what we're essentially saying is we take these, we form them into their elements, and then we recombine them to form this one. So it works that way. It's easier to understand that in terms of delta H or delta G, but that's basically how it works. So this, for this particular question, the entropy of the reaction is, the first product is this one, and there's only one of them. So we put in the 229.2 joules per mole K minus, all right, the first reaction is this one. So, and there's only one of them, 200.9 joules per mole K plus this one, and there's two of them, 2 times 130.7 joules per mole K. And for those of you who have taken General Chemistry 1 recently, and you'll remember that the delta H, and it turns out the delta G as well, for elements is 0, but the entropy is not 0. Okay, so that's basically how we do this. When we do this math, we find that it is minus 233.1 joules per K. Okay, since this is 2 moles, technically we don't need the moles here because we multiplied this by 1 mole and we multiplied this by 1 mole, so I made a little bit of a mistake with the units there. All right, and that is choice letter A right here. Now let's see if this makes sense, because if you notice, there are several positive answers. In these cases, they're written as positive, and this one, it doesn't show the positive. I don't know why. Let's see what happens. We have 3 moles of gas, okay, becoming 1 mole of gas. The entropy should be negative, right? We have 3 moles of gas, which is more disordered than 1 mole of gas, which is more ordered. So even if you didn't know how to do the math, it has to be this one or this one, because of the fact that, you know, the direction of the entropy has to decrease because we have less moles of gas on the product side. Number 9 says, determine delta G naught for the reaction of the following reaction at 385 K. And we're given this, and we're given the delta H and the delta S of this particular reaction. Since delta H and delta S are both positive, we do know that this reaction will be spontaneous at high temperatures, but we don't know how high of a temperature that is. We don't know, for example, if 358 K is a high temperature. So to solve this, we're going to use delta G equals delta H minus T, delta S. Okay. Note that, as usual, this is in kilojoules and this is in joules. So we need to write this as 0. Divided by 1,000 and write it as 0.1602 kilojoules, it should be up there, per K. Now we can plug in. Delta G of this reaction is equal to delta H, 179.2 kilojoules, minus T, which is given 358 K, times delta S, which is 0.1602 kilojoules per K, like that. All right, and when we do that, we find that the delta G of this reaction is equal to 121.8 kilojoules. So what we find is that this is not a high enough temperature for this to be spontaneous, because this is a positive value. All right, so we would need a higher temperature in order for this to be a spontaneous process. Question number 10 says, in the Haber process, ammonia is synthesized from nitrogen and hydrogen, and we're given the reaction. It tells us the standard delta G at 298 K for this reaction is minus 33.3 kilojoules per mole. The value of delta G at 298 K for a reaction mixture that consists of 1.9 atmospheres of nitrogen, 1.6 atmospheres of hydrogen, and 0.65 atmospheres of ammonia is. So this is looking at the difference between delta G at the standard state as opposed to delta G at current conditions, which are not 1 atmosphere of pressure of all of these things. So in order to find that, we have to use the equation delta G equals delta G naught, the standard one, which is given to us, plus RT ln Q, where Q is current conditions. Specifically, it's the pressure of this squared divided by products over reactants, divided by the pressure of this times the pressure of this cubed. So Q is equal to the pressure of NH3, the product, squared, because there's 2 of them, divided by the pressure of N2 times the pressure of H2, the 2 reactants on the bottom, and H2 is cubed because there's 3 of them. All right, so when we plug in the numbers, we find that this is 0.65, that's atmospheres, squared, divided by 1.9, again, atmospheres, I'm not writing the units to save space, times 1.6 atmospheres, the pressure of the hydrogen, cubed. And when we do that math, we find that Q is 0.054. So now we can come back over to this other equation and we can plug in. Delta G equals the delta G naught, which is minus 33.3 kilojoules per mole, plus R, which is got to be in kilojoules, so not 8.314, but 0.008314 kilojoules per K, times the temperature, which is given in the problem, 298 K, times the ln of Q, which we just found, 0.054. When we do all that math, we find that delta G is equal to negative 40.5 kilojoules. All right. And when we look through here, we see that the answer is choice letter E. I'm not sure why there's not units. Number 11 says, give the name of the reaction that achieves the theoretical limits with respect to free energy in thermodynamics. Now, again, this is like the other one that's kind of like something you just memorize. I'm not actually going to put this on the test, but a reversible reaction is the type of reaction that achieves the theoretical limits with respect to free energy. The reason for this is because the process is going back and forth, and therefore, if it were an irreversible process, generally you're losing a bunch of heat or paying a large heat/energy tax, making that process irreversible. For a reversible reaction, you're paying the least, I guess theoretically none, but practically you can't pay no heat tax. So basically, that's the answer to this question. It's just a definition. Number 12 says, calculate delta G naught reaction for the using the following information. We're given the delta G, the Gibbs free energy of formation for the products and the reactants, with the exception of nitrogen, which is an element. So this is very similar to the one that we did with delta S, where it's products minus reactants, or you may have done with delta H, both in this chapter and in General Chemistry 1. So delta G naught of the reaction is equal to the summation of products minus reactants, N, the number of moles, times delta G naught formation of the products, minus the summation of N, the number of moles, times delta G naught of formation of the reactants. Okay, so this is for the formation of 1 mole. If you form, well, this is, we'll think about this. Water, this is the formation of 1 mole. If we form 12 moles, it's going to be 12 times this amount of energy. Also, we need to notice that we have the element nitrogen. The Gibbs free energy of formation of elements is 0. So that we're not given that, and there's a good hint that it's 0. So now we can just plug in the numbers. Delta G naught of the reaction equals the products. So the first product is nitrogen, which is 0. So the second product is water, and there's 12 of them. So 12 times our minus 237.1 kilojoules. All right, and if you want, you could put this as 12 moles and this kilojoules per mole. You'll get the same thing. Minus our first reactant, there's 4 of them. 4 times minus 73.5 kilojoules, plus our second reactant, and there's 5 of them, 5 times 149.3 kilojoules. Can't see that. All right, and when you do all that math, you find that delta G naught of the reaction is equal to minus 3,298 kilojoules. All right, and the answers are in scientific notation. So minus 3.298 times 10 to the third kilojoules. So we have the decimal point here. We moved it over 3 times, and we got that, which is here, choice letter B.